Introduction to Molecular Orbital Theory, Part 2, the hydrogen diatomic molecule. Okay, so before we really get started, we need to remind ourselves of wave functions. So remember that electrons behave as waves in atoms. And remember also that orbitals are mathematical equations that describe the wave behavior of one or two electrons in an atom. Okay, so that's from Unit 6. Now, wave functions in molecular orbital theory describe overlapping atomic orbitals. So, for instance, in the hydrogen diatomic molecule, the 1s orbital on one hydrogen overlaps with the 1s orbital on the other hydrogen atom, and these two orbitals interact to form two new molecular orbitals, or MOs. Now, how do we do this? How do we mix this? How do we form these molecular orbitals? And so we mix these 1s orbitals on each hydrogen atom together. Now, how many molecular orbitals will we get? We talked about this in the first video. So if we mix two atomic orbitals together, then we're going to get two molecular orbitals, right? And when we mix, we're actually doing something called linear combinations of atomic orbitals, or LCAO. Now, you don't need to know how to do that, but that's what's going on behind the scenes when we mix these atomic orbitals. Now, the first molecular orbital formed in this mixing is adding the two 1s wave functions together. So remember, a wave function is just a mathematical equation for this orbital. So if we add those two together in the so-called plus combination, then we're going to get a sigma bonding molecular orbital, or a sigma 1s. And so here's the sigma telling us it's a sigma interaction, and 1s gives us the orbitals that form this molecular orbital. Now, the second molecular orbital is formed by subtracting the wave functions. So we're going to take the first 1s and we're going to subtract the second one in the so-called minus combination. And from this operation, we're going to get the sigma anti-bonding molecular orbital. And the symbol for that is, again, a sigma, and this star, which indicates anti-bonding, and then the subscript 1s, which tells us which atomic orbitals were mixed to form this. So remember the energy state diagrams that we were writing for multi-electron atoms in Unit 6. We ranked the orbitals in order of energy. So here's the 1s at the lowest energy. Next one is the 2s, then the 2p's, 3s, 3p's, and then the 4s and the 3d were similar in energy. Okay, so that's from Unit 6, and that's for multi-electron atoms. Now we're going to start building a molecular orbital energy state correlation diagram. And we're going to do it first for hydrogen, and later on we'll do it for other diatomic molecules. So here's the 1s on one of the hydrogens, and this subscript A just indicates this is hydrogen A, here's hydrogen B. So we're just labeling them. All right, so here's the 1s for that hydrogen, here's the 1s for the other one. And notice the diatomic molecule is here in the center. So what we're going to do is form the molecular orbital. This is the sigma bonding molecular orbital. It's going to be lower in energy than either of the two atomic orbitals. Okay, so it's lower in energy, it's more stable. And then the anti-bonding combination is going to give us the sigma star 1s, and that's higher in energy than the other two. So the bonding molecular orbital is actually lower in energy than either the two atomic orbitals separately, which is why it forms. Now, when we take the two valence electrons, so each hydrogen had one valence electron, when we fill this molecular orbital correlation diagram, then we're going to put both of them in the lowest energy molecular orbital. So we're going to follow our filling rules. And so when those two electrons are in that molecular orbital, then we say that they're bonded. Now, note that the sigma star 1s does still exist, but in the ground state there are no electrons in it, so it just hangs out. Okay? So this is our occupied molecular orbital, and it's a bonding interaction, a sigma bonding interaction. Okay, so let's talk about forming the sigma bonding molecular orbital. So here we have the 1s for each of the hydrogen atoms. And notice that I have a plus in here. That just indicates the phase. Okay, so the phase of the wave. So they're both the same. And when we overlap these two atomic orbitals with the same phase, then it's going to result in just constructive interference. And so that's a good thing. That's lower in energy, so constructive interference, and we're going to have the molecular orbital formed where we have both electrons delocalized over the entire molecule. Now the anti-bonding molecular orbital is a different situation. So now we have positive phase on one of the hydrogens, hydrogen 1s orbitals, and negative on the other. So when we overlap those, then we have destructive interference going on here. Okay, and so that cancels out the amplitude between the two nuclei. So this dotted line here is called a node, and that means there is 0 electron density in that region. And notice that the two sides, on each side of the node, we have some electron amplitude left. So we have some amplitude of the wave left, but one is positive phase, one is negative. Okay, so let's go back to the molecular orbital correlation diagram. And so I'm showing only the molecular orbitals for hydrogen now. I've taken off the atomic orbitals that were there. We're just looking at the molecular orbitals. Now, hydrogen has 2 valence electrons. So hydrogen H2, the diatomic molecule, has 2 valence electrons. And we're going to fill in the molecular orbitals with electrons just as we did for atoms. And so we're going to start at the lowest energy, and we're going to fill until we run out of electrons. So here they are. Now, we have to make sure that we follow the Pauli exclusion principle. So no 2 electrons can have the exact same 4 quantum numbers. So that means that one of them has to be spin up, one has to be spin down if they're in the same orbital. We can put 2 in an orbital. And also remember Hund's rule, which won't apply in this particular example, but later on we're going to have to remember that. And that's where we keep electrons unpaired until we have to pair them, and they need to have the same spin if they're unpaired in degenerate orbitals or equal energy orbitals. Okay, so let's promote an electron to this sigma star. So that means we're going to put a little bit of energy in this. We're going to take one electron to that higher energy orbital. And we call this an excited state. Now, for molecular orbital theory, we can write electron configurations just as we did for multi-electron atoms. So if we want to write the electron configuration for the diatomic hydrogen, which this should be H2, by the way, then we're going to start at the lowest energy. We're going to fill our electrons, and so that's done right here. And then if we want to write the electron configuration, the molecular orbital electron configuration, then we write sigma 1s, so that's the orbital that we're filling, and we put 2 electrons in there. Okay, so now let's write the molecular orbital electron configuration for the hydrogen diatomic molecule in the excited state. Okay, so here's an excited state, so write the electron configuration. Okay, and so yes, we would put sigma 1s, we have 1 electron, so the superscript 1, or you can just leave it off, but often you'll see that there, and then we put 1 electron in the sigma star. Okay, so we can also calculate bond order for ground state diatomic hydrogen. And so to do this, we're going to calculate it as 1/2 of the number of bonding electrons. So those are any of these MOs that aren't antibonding, so they don't have a star. So we're going to take the bonding electrons minus the antibonding electrons and divide it by 2, basically. And so for ground state hydrogen, then we're going to have 2 bonding minus 0 antibonding, none of them over here, divided by 2, and the bond order is 1. And that agrees with the Lewis structure. Okay, now what about our excited state? So if we take our 1 electron bonding, subtract off our 1 electron in the sigma star, divide that by 2, of course this is 0, so 0 divided by 2 is still 0, and we have a bond order of 0. So what does that mean? And basically it just means that there isn't a bond present. So this excited state isn't stable. Okay, so determine whether the hydrogen diatomic molecule with a charge of -2, okay, determine if that is stable. All right, so we have the 2 electrons from hydrogen, H2, and then the 2 extras, so that's going to make 4 valence electrons. And if we fill these guys, then we're going to fill up both of these MOs. If we calculate the bond order, because that's how we're going to determine whether it's stable or not, then we're going to take our 2 bonding electrons, subtract off our 2 anti-bonding, divide 0 by 2, of course, and we're going to get 0. And so what does that tell us? It tells us that that species is not stable, so it wouldn't stay together. Now, what about helium diatomic? Okay, so count your valence electrons in helium, and we have 4. So basically we get the same answer as we did for that anion that we just looked at. And so we have 2 bonding electrons minus the 2 anti-bonding, and so the helium diatomic molecule is not stable. That is the reason why we don't see it. So remember, helium is a noble gas, and it's not found in nature as a diatomic molecule, and that's why. Okay, so the next thing we're going to do is MO correlation diagrams for homonuclear diatomic molecules. And so we're going to be looking at the second period, and there are 2 different correlation diagrams, first and second order, and we'll be discussing those.